So we were talking about Benedict's test, and the thing about Benedict's test is that it's for identifying hydroxy ketones or hydroxy aldehydes. Let's see if this works. This is what I've been having trouble with. Let's try it. Oh yeah, good, it's working. So that's the hydroxy group. Oh, you know, I'm going to leave this open in case the students need me for something. And what you're doing is you're doing the oxidation reaction of an aldehyde. And what we learned in the last chapter is when you oxidize an aldehyde, you get a carboxylic acid. In the Benedict's test, this is coupled with copper 2+, and then what you end up getting is copper oxide. And when you do that, it turns red. Okay, so some of you actually did we do Benedict's test this other day? No, we didn't. We will be doing it soon, though. Okay, so Benedict's test does that. So now, if you look, some of the kinds of things that we use it to analyze, we used to look for glucose. Remember I talked about my doctor tasting pee? Yeah. We use it to determine if there's sugar in urine. We use Benedict's reagent, which is shown here as the copper 2+, which is the blue solution, right? When it reacts with glucose, are you guys familiar with this kind of drawing? It's just a Lewis structure that's going up, right? And then this is the aldehyde functional group. There's the OH, so this is the hydroxy aldehyde. When this oxidizes, this hydrogen gets replaced by an OH group, okay? So that's the oxidation of glucose to gluconic acid, which is down here. Questions? Okay, so I'm going to skip over. Now, aldehydes, we talked a little bit that aldehydes can be reduced, so can ketones. When you take an aldehyde and you reduce it, that's the opposite of oxidation. Oxidation, you add bonds to oxygen, and reduction, you remove bonds to oxygen and you add hydrogen. So you can add hydrogen to aldehyde and you end up with a primary alcohol. And you can add hydrogen to ketone and you end up with a secondary alcohol. Okay? You guys see that? Any questions? I'm coming out of one frantic world into this one, so I'm trying to I can't quite tell if it's just me or if it's you guys. It seems really, all of a sudden, very slow paced to me. Okay, so what we're going to do is we're going to write condensed structural formula and the oxidized product of each of the following when mixed with Tollin's reagent. Okay, so Tollin's reagent, if you remember, is the silver mirror test. It detects simple aldehydes. Okay. So, butanol, what does that mean? How many carbons? 4. So you're going to go 1, 2, 3, 4. And anytime you see condensed, I'm going to do bond line, but you can do condensed as well. And that's okay if you do bond line as well. And then, what does the suffix al mean? Aldehyde, right? So it looks like this. So Tollin's test reacts with simple aldehydes. It's oxidation. This is actually exactly the same as you would have done it in the last chapter. And I'm going to end up with 4 carbons. And then what do I change? The hydrogen becomes an OH, right? So there's the oxidation product of that. If you did the condensed structure, you would have a CH3 here, CH2, CH2, and then CH and O, and then it goes to CH3, CH2, CH2, and then how do you write carboxylic acids? COOH. Yeah, 2 O's because of the 2 O's that are on there. Okay, so that would be the condensed structure. Acetaldehyde, what's this acid mean? 1 or 2 or 3? What is it? 2. Form is 1, right? Acet is 2. Propion is 3. Butyryl is 4. Valor is 5. And then capro is 6. Okay. So then what I'll do is to do this, I'll draw acetaldehyde, 2 carbons, and then an OH. Or in the condensed structure, it'd be CH3 and then CHO. Forgot the C. Again, it's an oxidation reaction. So what happens to the product again? Yeah. Get that H, make an OH. So the condensed structure is CH3COOH. I think it's easier to learn these things as bond line, and it's totally acceptable as an answer. And then once you do the bond line, you can translate that back into a condensed structure. But to see what happens, bond line is the easiest way. So ethyl methyl ketone, all right? There's the ethyl. There's the methyl. So that's ethyl methyl ketone. What does Tollen's reagent do with that? It's a ketone, right? Tollen's reagent only reacts with aldehydes and doesn't react with ketones. So for this, there'd be no reaction. Why? Oh, because in order for you to be able to, going back to what we said in the last chapter, in order to oxidize a carbonyl, you have to have a hydrogen to replace. This doesn't have a hydrogen to replace, and so there's no reaction. Okay? It's not that you can't get it to happen, it's just not going to happen with this reagent. Okay?
On B, whatever, why did you say was the reason that you wrote it that way rather than the other way or something?
Oh, I just like doing it this way because I think it's a lot easier to see what happens when you do this to this than when you do this to this.
Oh, okay.
Right? And so when you're learning it, I think it's better to, because you can just see, oh, the H is replaced by an OH.
Yeah.
That's much easier to remember. Then you just translate that into a condensed Lewis structure. The question actually says, right, condensed structure, structural formula. So that's what's at the bottom of each one.
So what was the part that you said about how you know about how many lines you can do that?
Okay, so in acetaldehyde, the ACET, right? That means 2. So there's form, acet, propion, butyryl, which I gave you actually, I think, before. Yeah, you just have to memorize those. Yeah. So that's how I need to draw 2 carbons. Questions? We're in week 5, huh? Man, 13 more to go. But 3 more till we start prepping for that at the 9th week, right? 4 more till the OChem final. So we're going to be through all this organic chemistry. So just saying, that should be an encouragement. Okay, I just made some extra slides. So that's actually the problems. I spaced them out in case I needed more room to write, but I realized I didn't, so I skipped them. All right, predict the product for each of the following reactions. Now, that reagent, right, you see hydrogen and platinum, a metal. It's all kinds of metals will do this. But that means if I have hydrogens here and I'm adding it to this, it's a reduction reaction. Okay? So in a reduction reaction, at each end of the double bond, you're going to add an H. So I'm going to go ahead and do a condensed structure since that's what they gave us for this one. Okay, now, real quickly, let's make some notes on this for you. Since I'm going to add a hydrogen at each end, that means I'm going to have to attach one here, attach one there. Okay, so that means one here and one here. So that's the primary alcohol.
So to condense it, you could put CH2.
Yeah, yeah. But that was just so you could see without adding. So the condensed structure, if you're writing it out, CH3, CH2, CH2, and then OH is usually how we put the alcohol function.
And you always remove that double bond from the O.
Yeah, so this double bond here, I get rid of it and I put a hydrogen at each end. So when I break this double bond and make it into a single bond, each end of this bond has to attach to something. Sorry. So it's a little trickier to see, but this is sodium borohydride, and again, it does the same thing as H2 does. It's the reduction reaction. You know, you can kind of know that just because the reagent has hydrogen in it. So what I'm going to do when I reduce this, is I'm going to add a hydrogen at this end and a hydrogen at this end. Same thing, okay? So I'm going to add one here, and I'm going to add one there. So, you know, this is R. If you want to think about it, this is R. I haven't looked at your final, but go ahead and memorize these reagents for now. It may be that on your final they just expect you to know that it's oxidized and reduced, and I'll let you know that before you take it, so you don't have to memorize a bunch of random reagents, okay? Okay, so.
Those are 4 H at the end, right?
What's that?
It's a 4 at the end of the H.
Yeah, sorry. I obliterated it. So I'll draw this bond line. I have my O. And then on each end of that double bond, I'll put an H where it was, like that. So take a ketone, you do a reduction reaction, and you end up with a secondary alcohol. That happens whether, and you could put H2 and platinum on this arrow. You could switch the reagents on this arrow. They both do the same thing, okay?
So even though it's H4, you would just take H2 and 2 of them?
Yeah. Okay, questions? How that's going? Well, that's it for that section. Hang on. Just a little side note. We're going to be talking about hemiacetals and acetals. And what the reason these are important is this kind of bonding is how monosaccharides, what's a monosaccharide? Mono means one sugar, right? How monosaccharides make polysaccharides is through these bonds that we will classify as hemiacetals and acetals. So in maltose, it's actually an acetal bond link between two glucose molecules. So maltose, that like malted flavoring, is actually just two glucose molecules bonded together. And what we'll learn is how they bond to each other, what the structure is, okay? And then part of what we're doing is we're learning how to draw these things, either as condensed or bond line, they call them line angle structural formulas. Okay, so I made the slide up. Hopefully it makes sense. What does hemi imply? Half, yeah, like a hemisphere, right? It's 1/2 of a sphere. So hemiacetal is half an acetal. So let's sort of start up here and look at hemiacetals. It says appear as a carbon with both an ether and an alcohol functional group on the same carbon. So this is the ether, and this is the alcohol. The acetal bond is actually the COR bond, right? So an acetal just has two ether groups on it, okay? So this, you can recognize an acetal because you have a carbon and it's bonded to an oxygen, and the R, you're familiar with the R notation, just another carbon. It could be anything. It could be a methyl group. So R equals like CH2 and then something else. The way we use the terminology generally is, colloquially, how we just say it, R just means the rest of the molecule, and I just didn't draw it, okay? But it's usually something with a carbon, so it's one ether to a carbon and an OH group, that's a hemiacetal, and then two ethers is an acetal, okay? So let's try something. I'm going to make something up. What is that? Is it hemiacetal or acetal? Hemi, right? Because I have the ether here, and I have the alcohol here. If it was going to be an acetal, I could have to have another ether group that's down here. So this is an acetal, and this is a hemiacetal, okay? So let's see how these things fit into different structures, okay? So we use these reactions for a lot of different things. They list them out here, but we're not going to go into all those things. Here's an aldehyde. So you start with an aldehyde, usually an aldehyde, because aldehydes turn out to be more reactive. And you react it with an alcohol, and you'll notice what happens. It looks like, at least, that this alcohol molecule gets split up into two parts. There's the one part, okay? And then the other part, this H, that's here, right, gets attached to the oxygen that's down here. So this group here attaches here, and then this hydrogen attaches down here. So this is a hemiacetal, if you recognize it now. There's a carbon, oxygen carbon, so it's an ether. Then down here, it's an alcohol. So that's the hemiacetal. It's usually done with an acid catalyst. If you do it again, so you start with H plus and another alcohol, then what you end up doing is replacing this whole group, okay, with this. So this part replaces this part. Now you notice that this has a hydrogen on it that's not being used, and this has a hydrogen on it that's not being used, and an oxygen. So that's what the other product from this reaction is water, okay? So start with aldehyde, hemiacetal to an acetal. Now, ketones can do this, but they do it less often, okay, just because they're not as reactive. Yeah, I'll get to it later. I think this is just the same thing again. Just another example. You can do it with ketones as well. Having connection problems again. All right, here's an example with a ketone. And in the ketone, I'm going to attach this part of the molecule, and the hydrogen is going to go in the other part. So you can see that in the product. I've added this, and then here's the hydrogen that came from it. Okay? And if you do it again, there's another molecule that gets attached. That adds the second group that's down here, and then the other product is water again. So the pattern is alcohol, split it apart, attach it, right? And then take a second alcohol and attach that. So that's where this ether comes from. This ether comes from the alcohol. All right. I'm sure there's questions. Like,
Is there water always at the end?
what's that?
Is there water always at the end?
Yeah, there's always a water molecule that comes off the end. That's where the oxygen of the original aldehyde or ketone goes to the water.
Is there water that's formed when it turns from a ketone to a
No. So because in here, right, you're adding an oxygen. Here you're adding an oxygen, but you only have two left, so you got to do something with the
So
oxygen.
there's no other second product when it goes from an alcohol to the...
No. Yeah, so in this first product here, that's all that's formed from this. And then what they're saying is you add another one and you get this, but then you have to it has to be a water molecule. Yeah.
Where did the H2 and the H2O come from?
So, yeah. So you notice here I have an OH, right? And here I have an OH, but I only for this I only need one oxygen.
Oh, okay.
So I use this oxygen, that leaves that hydrogen left, and then this whole thing has to come off. Right? So this is actually in here, and then this accompanies it and goes there too. And that's where you get the H2O from. Okay, so another important class of compounds is cyclic hemiacetals and acetals. Anybody know where this is important? Where do you see this kind of thing? It says sugars, but in glucose, for example, like glucose is a sugar, right? It's like the most common energy source for your body, basically. It breaks things down into glucose a lot. You normally find glucose in your body in a ring form. The reason it's in a ring form is it starts as an open chain like this and then closes to form a cyclic hemiacetal. Turns out this structure in solution is more stable than this structure. Okay, so how does it form? It's a little bit tricky to do these, okay? But you'll notice that they put numbers here. It's not for nomenclature, but what they did was they numbered everything that was going to be in the ring. So start at the aldehyde and number 1, 2, 3, 4, 5. And if you want to, go 6 like that. That means when this hemiacetal forms, it's going to form a 6-membered ring. So the easy way to draw this, or to know what to draw at the end, is to draw a 6-membered ring. That's the hexagon shape. Looks like chicken wire or honeycomb from a beehive. You draw that. And then you just place the oxygen in it. You could be anywhere, but that spot in the corner is traditionally where the oxygen goes. It's like where we normally draw it. Okay? You'll notice when we look at pictures of glucose and all the other sugars, the oxygen's always in that top right-hand corner. That's the way we've drawn it. Now, this oxygen, okay, let's go. I'm going to go back one slide just to show you something. Look at this oxygen here. That's the carbonyl. Here's the carbonyl. The alcohol comes in, but what functional group does this oxygen become? It becomes an alcohol. Okay? So where the carbonyl group is eventually becomes an alcohol. So back onto this drawing, right? That's the oxygen. It's going to become an alcohol. There's the alcohol that comes in. This is going to become the alcohol. So when it comes in on this cyclic hemiacetal, there's the OH group of the cyclic hemiacetal. So on this bottom of this diagram, we're drawing it down like this. It doesn't have to be drawn down. It can be drawn up or down. It doesn't matter. Well, it matters, but it doesn't matter for this kind of drawing.
I have a question
What's that?
on the open chain.
Yeah.
How will we know when looking at things like that when it's, say, 5 carbons and that last line is just aligned to the substituent versus counting all the way to 6? Sometimes you say, oh, that's not an extra carbon, that's just.
Oh, okay.
one.
So in these structures, this oxygen becomes part of the ring. Now, in the naming, you would only go to 5. Okay. But if you're trying to figure out how big of a ring to put, you have to count from the carbonyl all the way to the oxygen. So I'll show you. Let's do a different one. Let's do this. Oh, I'll make it even more fun. Well, let's not make it more fun yet. Let's make it more fun next time. Okay, so that's my molecule I'm going to start with. How many atoms go in the ring? 5. The way you do that is you go 1, 2, 3, 4, 5. Okay? And then you're going to make a 5-membered ring, which is a pentagon. And traditionally, when we do these in biology or biochemistry, is we put an O at the top. Okay? That O is the number 5. So this has to become an alcohol, right? So this 5 comes around, it attacks over here or attaches over here. If you want to call this 1, it doesn't matter which one you call 1, but traditionally that is the number 1 on the right-hand side. There has to be an alcohol functional group there, so you could go like that. Now, in fructose is a ketone sugar. And so it has, instead of an aldehyde at that position, it actually has a ketone. So let me show you another example that's more relevant to like the biochemistry we're coming up to. So I'm going to make something similar. So now I'm going to make a ring, but I go from the carbonyl group to the oxygen of the alcohol. So I still have 5, right? So again, just the practice of going through 1, 2, 3, 4, 5. For nomenclature, you would have stopped at 4. But for just trying to figure out what the product is, you stop at wherever the last thing is. So in this case, it's the oxygen. So I'm going to make, again, a 5-membered ring. Now, on the this is 5, this is 1. On the number 1 carbon, I'm going to have an alcohol functional group, right? That's this one over here. Sorry, that's that one there. That's that one there. So when this oxygen comes in, it attaches itself here. This becomes an alcohol. I'll have to have an alcohol functional group here like this.
Will that always be on the number 1?
Yeah. Yeah, because that's where the carbonyl is. Wherever the carbonyl is where the alcohol functional group ends up. So you bring an alcohol in, you take a carbonyl, and you convert it to an alcohol. I know it's a little confusing, but just practice it a few times. It'll get better.
What about that methyl group?
Oh, yeah, I'm not done yet. So, and then in fructose, it has 6 carbons in it. So in fructose, there's always another carbon down here. And it's a methyl group. Okay. So when fructose makes its cyclic structure, and we call it a cyclic hemiacetal, when it makes its cyclic structure, on that number 1 carbon is always a methyl group and an OH group.
Okay, so since we added add in the extra hydrogen, why not?
Oh, it's still there, but remember in bond line, you don't always draw them.
Oh, okay.
Yeah, so you can go back, like, well, I can go back actually. I think I can go back. Like that one there, right? It's there, I just didn't draw it. Yeah. No, that's a good call, because people get confused by that. I'm just so used to just drawing, not drawing it.
This is the kind of stuff where it's probably gonna be easier on me if I it's just memorization, don't try to make sense of it, right?
Yeah.
It's just, that's
It-
the answer. It's
yeah.
just-
You're just gonna look to see the patterns and how things end up. Where does this oxygen go? What does this oxygen become? And once you have that down, when you start doing the biochemistry and you start looking at sugars and you start looking at the physiology and stuff that you guys will be eventually going on to or have already done, unfortunately, because it's always better when you do the physiology after this class, because then you look at molecules and go, yeah, I know that molecule. Okay. You'll recognize how those different structures form, and part of the idea is it makes it easier for you to learn all those molecules. Like, you guys have to do Krebs cycle? You guys know what Krebs cycle, and all those structures, right? If you had done some organic chemistry before, you would have looked at those structures and go, oh yeah, of course that's what that does. I'm adding carbons, I'm taking off carbons. There's a CO2 that leaves, right? That kind of stuff. All right, so this is the actual glucose molecule. This structure on the left is essentially a Fisher-like diagram, but it's a bond, it's a condensed Lewis structure of glucose. This is actually known as D-glucose, just for fun. The D comes from dextro, and that's why sometimes you'll see glucose called dextran or dextrose, okay, because of the D-glucose. D is the other version of this is L, okay. L stands for left, and D stands for dextro, which is right. And so that in the Lewis structure for D-glucose, the way we draw these, this is on the right-hand side. That's D-glucose. And then it's kind of like right, right, left, right. That's how you recognize it. Anyways, if you take this molecule and you tip it on its side, this oxygen that they've highlighted here comes around and attaches to this carbon here. So there's the double bonded carbon. They put it, the number 1 carbon is here, okay? Here's the alcohol off the number 5 carbon. Now remember, if you're counting for the ring, this would be number 6. This ends up in the ring. So this comes around, this 6, there's 6, 5 here and 6 carbon here. Here's the oxygen, it comes in, and then it forms a hemiacetal, okay? So this is the hemiacetal of glucose. They often call it a pyranose. That's an old name for it. They call it a glucopyranose. But that means it's the ring form of glucose. 99.9% of glucose in your body is actually in this form. Okay? When it stores as a polysaccharide, it stores in this form. Do you guys see number 6 up here? Right. He's up over here. That's this carbon here. All right. Now, you can form a bond between 2 sugars. Now, let me go back up for a second. Well, let me do this first, actually. So in order to form, there's a cyclic hemiacetal. In order to form the cyclic acetal, I just have to replace this. That's this part here with this part here. Okay, and the other part's water. Right? So when I do that, that forms this. Now, think about this. If you have 2 sugar molecules, okay, let's go back 1 slide. What do you see all over glucose? hydrogens and oxygens, right? In fact, there's 6 OH groups on there, right? Those can, 6, right? 1, 2, 3, 4. 1, 2, 3, 4. Oh, it's 5, sorry. 5 OH groups. Any one of those can actually form the acetal bond. So it's very easy to recognize, I think, that once you have this, and it's in the presence of a sugar that has a lot of OHs on it, that it can do this. Okay? All right. I'll show you what it looks like here in a second. Everybody sign in? I just realized, I keep having to look over there at my slides, and I realize, oh, wait, I printed all those silly things out. So this is maltose. Let's do this. I'm going to number these. This is 1 over here, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6, like that. So I numbered each of the rings according to how we were numbering them before. What carbons link maltose together? The 1 and the 4, right? So if you actually wanted to make this longer, right, you could actually see this is the number 4 carbon on this one, right? It has an OH group. You could attach it and make the acetal of this one too. If you keep just taking a bunch of, so maltose is just 2 glucose molecules bonded together in this, what's called a 1,4 disaccharide or 1,4 glycosidic bond. It's got a name. But the 1,4 that you'll see in a lot of the biology stuff comes from the fact that this comes from the 1 carbon and 4 carbon is connected to. But you can just as easily draw another molecule over here. I'm going to not draw the whole thing because it's going to look ugly. And I can link it like that. And that's another sugar we call residue, another sugar molecule attached. If you keep doing that, right, and doing that, and doing that, that eventually forms what we call, does anybody know? It's a polysaccharide, and it's amylose. So the sugar, like starch, simple starches, are formed when you take these like maltose-like units and just start linking them together over and over and over again. So amylose, which is the simplest of carbohydrates, is simply a long chain connected from 1 to 4 to 1 to 4 to 1 to 4, and it makes these long structures that are thousands and thousands and thousands of glucose molecules long. When your body needs energy, it burns glucose, right? So there's an enzyme that takes this and then chops it off sugar by sugar by sugar by sugar, and that's how you get the energy, the sugar out to get the energy from it. Where else do you think you could connect one? What's that?
The other side.
I can connect over here, right? And put another one over here. I can even connect to here. In fact, I can connect anywhere, but it turns out this is like the more reasonable place because it's just it's out of the way and the most exposed. So a lot of times in amylose, and the other one that you might be familiar with is amylopectin, you get connections from 1 to 4, but you also get connection from 1 to 6. Now, anybody know what the properties of amylopectin are in biochemistry? Amylose is like starch and sugar, right? Amylopectin is like, okay, who's an athlete in here? Who's done like training before? I haven't. I have children that are athletes. What do you do the day before a big event? Eat a lot of carbs, right? Carbo loading, right? And what you're trying to do is you're trying to make a lot of amylopectin, and that's an energy source. And the reason it's a good energy source is because of all the branching that it has. Like, think about it like this. here's a glucose molecule. I'm going to draw this like little tiny thing. It's a glucose molecule. It's connected to another glucose. It's connected to another glucose and another glucose and another glucose. Now remember what I said is like if you need energy, your body has to take this and digest it piece by piece by piece. But if you branch this, so this is 1 to 4, now this is 1 to 6, and you keep branching and branching and branching, again, these are all 1 to 6, 1 to 4s, right? You notice how many ends you're going to get if you keep branching? About every 4 to 6 carbons it branches. You get a lot of these little ends there, and when the enzyme goes to chew the amylopectin up, we call it glycogen in our body. It has lots of little ends to chew off of, and so it can get the sugar a lot faster that way. And when you can get the sugar faster, then you have more ready access to the energy. Okay. So identify a hemiacetal or acetal. Hemi. Why hemi? Because I have the OH, right? One's an OH and one's an ether. So what's B then? Acetal, because they're both, right? Ether, ether, this is ether, and this is alcohol. Oh, that's weird. Okay, so draw the condensed structural formula of the acetal formed by adding CH3OH to butanal. So we're going to draw butanal first. Oh, and it says draw the condensed structural formula. Like I said, whenever you see that, feel free to use bond line. So butanal is how many carbons? 4. Al is what? Aldehyde. I'll draw the H in because it is confusing if you leave it off. And I'm going to do the hemiacetal with CH3OH. Okay. Oh, it's for the acetal. So we're going to do this step by step, okay? And then we'll do the shortcut. So if I do the first step, I end up doing this. I get OH, H, and then CH, CH3. I drew it backwards because I don't like drawing it the other way. And then when you do the next CH3OH, you're going to get this. The H is still there, and now you have OCH3 down here too, like that. So this is the acetal, and this is the hemiacetal. What's the shortcut? How would you say, because it says acetal, how would you just know what to do there? You get rid of the oxygen, right? What do you add? 2 ether groups, 2 OCH3s, right? Yeah. Ooh, is that the end of that slide series already? Okay. Last but not least.
So
We're
to
in-
get to that hemiacetal, all you did was replace the H3OH and you just added that in there.
I just added that in there and made the C double bond O into COH, yeah. Gonna take a 2-minute break. I'm gonna walk off for a little bit. You guys can walk around. I need to go get a model kit. Do this properly. still need time because I got to make these. I always think that I'm going to have more time to do stuff during the day when I teach organic chemistry, but it's just so much work. I'll use these. There we go. Blue is a pretty color. Oh, what did they do there?
Is your son still sick? Is he feeling better?
What's that?
Andrew?
Yeah, he felt really good yesterday. He went to his first soccer practice ever and had a great time, and then he got home and he was sick. But when you get to go play soccer, you gotta feel good. I know not everybody likes soccer, but still. I just like my kids doing things rather than the opposite, which is not doing things. All right. Thought maybe I could have that stand up on something. No. Okay, I'm going to make another one still. Orange and brown and green. Oh, this one doesn't have the cool stand hole in it. Well, you're going to have to ignore that I have different colored bonds. It turns out I don't have enough of any color bond really to do this, except for maybe black, but who wants to do that? Okay. Oh, I recorded that break. All right. All right. So we're covering an important topic. So before I even get to the slides, I just want to sort of introduce this idea about molecules having different shapes. Okay, so you guys know what a structural isomer is? You guys learned that? That's when you take the same atoms, right, but connect them differently. So that's like Legos, right? You could make a house, you could make a spaceship, with all the same pieces. You can make little people, right? Those are constitutional isomers of each other. Same pieces, just stuck together a different way. Now, they're also called structural isomers, so I don't know what you guys were told before, but anyways. These are known as stereoisomers. So ignore the fact that the middle is red and the middle is blue. Just look at the spheres. Right, I have a white one, a brown one, a green one, and an orange one. And I have the same things over here. So these are definitely isomers of each other, right? Now, you notice they're all connected to the central atom. So you would say to yourself, well, aren't they the same? They're not, because spatially, they're arranged differently. See that? Once you have 4 different groups, this is the important part. Once you have 4 different groups connected to a carbon, okay, you can have what are known as stereoisomers. They are actually, if you look at them, like say there was a mirror in between, you see how one's the reflection of the other? Like there's that, and then on the ends, right, green on both ends. These are actually mirror images of each other. Now you might think this is like a really foreign concept, right? They're mirror images of each other, right? You don't have 2 left hands, no matter what anybody says. They're not the same. They are mirror images that are different. And we say it this way, mirror images that are non-superimposable. Which is funny because it looks like superimpossible when you see the word. But they're mirror images that are non-superimposable. So let's see, let me reorient this. Orange, let's put the green on this side. The green over there. Put the orange in the back, spin it around, spin it. Yeah, there we go. There's the mirror images, right? Now watch this. This is a trick. It's not a magic trick. I'm not going to make a $100 bill here. I'm going to take just this one and this one. I'm going to switch them. Now, I can't make mirror images out of them. You notice that? Because it's the same molecule. See how the brown and the green and the orange and the white line up? So that turns out, okay, so here's the thing. I'm just going to switch, and you can switch any two, doesn't matter. We refer to molecules like this very simply as having hands to them. They have handedness. Just like you have a left and a right, we actually will, you don't learn it in this class, but we learn about a left and a right-hand version of the molecules. And what these molecules actually do, one of the things that you'll see in the notation, you'll see this D and L. It turns out these molecules interact with light so that when light passes through them, they actually take the light and turn it in either the left-hand clockwise direction or counterclockwise direction. So that's where the D and L come from. D means it turns it to the clockwise direction. L means it turns it to the counterclockwise direction. So here I have these two molecules that are mirror images of each other, non-superimposable. These are known as stereoisomers. You only get that when you have you can only have that, I should say, when you have 4 different groups attached to a carbon. Okay? 4 different groups. Your book is showing on the slide now. Let's sort of get into the slides. They're showing that things like gloves, right? Because your hands are in the glove. Things like gloves are chiral. Things like baseball bats are achiral. Chiral means handedness. Okay, so there's not you don't have a left-handed and a right-handed baseball bat. Which, by the way, if you've ever coached baseball, which is one of the standard things you tell children, oh, did you get the left-handed baseball bat? With technology, there may be such a thing as a left-handed baseball bat, but. Okay. By the way, if you were able to take your thumb off of one side of your hand and put it on the other side, then it would roughly represent achiral, because you would have 2 left hands then, right? So what we're going to try to do is identify chiral and achiral carbons in different organic compounds. I'm going to skip a lot of the slides that they showed here. Sorry, guys. Because I just did it with hands. By the way, right, shoes are chiral. A mug, like a glass like this, that's perfectly symmetric, is achiral. Right? And again, any carbon that has 4 different groups on it can be chiral, and that means there's 2 versions of it. There's a left-handed version and a right-handed version. That pair are called enantiomers. That's the word. Oops. I somehow clicked slides that I should not have. Hang on. So enantiomers, that's the term. So what I'm going to do, like a blank slide, we're going to draw the molecules, okay? And we'll draw some molecules and we'll try to figure out which carbons are chiral and which ones are not chiral. Okay, let's see. CH3, CHOH, CH3. And I'm going to do this, CH3, CHOH, and then CH2 and CH3. And then I'll do some bond line as well. Okay, so what we want to determine is whether or not it's chiral or achiral, okay? So if you look at that top left molecule, the one that's up here, and you say whether or not is it chiral or achiral, this carbon, the rule is chiral, 4 different groups. Okay, so I have a hydrogen, right? And then I have a hydroxide, an OH group, but then I have these groups. You notice they're the same, right? So chiral or achiral? Achiral. Two butanol, that's on the right. What do you think? Chiral or achiral? So you go through, I have that and that, those are different. Chiral, because the groups at the end, this one and this one are different, okay? So there's my 4 groups. So this one is chiral. What about, here's a bond line drawing. And when you do bond line drawings, draw the hydrogen in when you're doing these. Sometimes they don't draw them. And if you're trying to determine whether or not it's chiral, it's important that you have the hydrogen drawn. Chiral or achiral? Chiral. Yeah, chiral. Because that's a CH3, CH2, CH3, H, and a Cl, so it's chiral. It's got 4, the rule is 4 different groups. What about the one on the right? What? Oh, this is a CH2, CH3.
And you automatically know that just like memorization?
Yeah, from practice with bond lines. Yeah. So, so then what are these then? Achiral, and this is CH2, CH3, but this is CH2, CH3. Okay? Doesn't matter what direction it's drawn, right? It's the same group. So these 2 groups are the same. That makes it achiral. And this one is chiral. 4 different groups. And again, the underlying groups here are the same. What's that? Yeah, right? Not bad. Well, and the acetal and the hemiacetals, not horribly bad either. You just have to practice at it. It's just like anything else. The more practice you get at it, the better. Okay, so let's look at these. MSG, right? That's our friend. Maybe not your friend, but it's my friend. I was like raised on this stuff, and I heard it was horribly bad for us, and we couldn't use it anymore. And then I heard it's not so horribly bad for us. So I don't know which is true. I did stop eating it for a while because they said it was horribly bad. And then I realized I was Asian. And it was like a sin against my grandmother. Yeah, we eat some weird stuff. So, anybody else here fight over the fish's eyes? Yeah. Not a lot of people love. Yeah, we used to fight over the fish's eyes because we liked the little bone that was on the inside, and we would save those. They were cooked. Really? All right, so MSG, chiral, achiral. Chiral. There's an acid group here. There's all this other junk over here, right? An NH2 and an H. Right? By the way, this is related to the amino acid neurotransmitter, glutamic acid, if you guys have heard of that, or glutamate. It's just got a sodium in place of the hydrogen here. And then this is glycerol, which is at relay, or glycerin. You buy it at a store. It's called glycerin. It's the stuff you put in the fancy soaps and stuff. Chiral or achiral? Achiral, because these two sides are exactly the same, right? Good. So I'm going to teach you something called a Fisher projection, and this is something that we'll have to get used to doing because it comes up a lot in biochemistry. And a Fisher projection is me running after you like this. I'm going to give you a hug. Okay, so if it's on the sides, it's going forward. If it's going up and down, it's behind. Okay? Like when you go to give somebody a hug, you don't do this. Well, mine. It's a police officer. But yeah, your arms go in the front, right? So that's a Fisher diagram. And in a Fisher diagram, what it says here, it's a two-dimensional representation of a molecule. Most often we use it for chiral molecules, okay? Vertical lines go back, that's or in the back. Horizontal lines go forward, and you'll see them drawn like this, just like that. So these ones, I'm going to do this forward and then back. It represents something like that orientation. You notice how these go back from the central, right? And these go forward. Now remember, these, when we last left our molecules, they were enantiomers, right? So what I'm going to do is I'm going to draw these on the whiteboard because it's a lot easier for you to see it on a whiteboard because I'm going to hold it up and draw it. I'm going to put the green at the top, like this. Remember, goes back, so it's this orientation. To have green, orange, and then white and brown. Okay? So that would be the Fisher representation of me holding the molecule in this direction. I wish I could stick that there, but I can't. So I'm going to do this one now. I want green and orange to go back. So that's the orientation. I'm going to draw the other one. This is a pair of enantiomers now. This is one of the molecules. This is the other, okay? So I have green and orange going like this. And then what do I have on the left? I have white and I have brown, like that. So that's the Fisher representation of the two molecules. Remember, those two molecules were mirror images of each other, right? What are these drawings? They're mirror images of each other. So Fisher representations of molecules allow us to show the stereochemistry of a molecule without getting too crazy about the way we draw them. And this is the style of drawing Fisher, the guy who these things are named after, or who named them, used to determine all the structures of the sugars, because they were so complicated you had to have a simple way to represent the sugar molecules. Okay. So it turns out this molecule on the left is known as glyceraldehyde. It says right here, actually. This is glyceraldehyde. That's a we're going to do a Fisher projection of glyceraldehyde. What they're trying to show is that the C double bond O is going back and the CH2OH is going back. That's what the dashed lines represent. And the wedges mean that they're coming out towards you, like they're zooming out at you, okay? So in a Fisher diagram, you take the bonds that are going forward and you place them left and right, and you place them on the left and right hand sides of the cross of the fissure diagram. The thing that's not drawn there, which is often very confusing, is this. And you can see that in this fissure diagram, this carbon is chiral now because it has 4 different groups attached to it. It's a nice, easy representation. So in glyceraldehyde, which is the simplest of the sugars, on the left-hand side, if you put the OH on the left, that's L-glyceraldehyde. And if you put the OH on the right, that's D-glyceraldehyde. Okay? Anybody know what all the sugars are that we consume in our bodies? They're all the D form. That bottom, this group here, and all the sugars that we are able to use is on the right-hand side. And the left-hand side ones don't do us any good. Some of the artificial sweeteners, yeah, they've switched some of the H's and OH's, so we can't metabolize them. And they're still sweet. And what's neat about them is they taste sweet to us, but bacteria can't utilize them either. So people who chew the gum that has some of the new what's called alcohol sugars have less tooth decay because the bacteria get scrubbed off by the gum, plus they can't consume the sugar. So, although I should warn you that some of the sweeteners are actually like laxatives because you can't use them, and so yeah. Sucralose is one of them. You'll see that in a lot of gums. There was this one poor lady, it's documented in some medical journal, but anyways, this one poor lady who had diarrhea for like 6 months. And the reason she had diarrhea for like 6 months is she kept chewing gum because she felt bad. Think about that. So she had this artificially sweetened gum. She was chewing so much of it that it was giving her diarrhea.
Probably quit smoking.
Yeah, it could be. That would be awful. Anyways, yeah, then they figured out, stop chewing gum, you'll be better. But I bet she had great teeth. All right, sorry. All right. So you can also have 2 or more chiral carbons in a molecule. So we're going to draw or show the drawings for erythros. And in erythros, there's 2 chiral centers. So the 2 chiral centers, I'll highlight them in red, I guess. Orange, red. Ooh, I got a nice red color. That's there, and there. There. So in erythros, which is a 4-carbon sugar, the L stereoisomer, again, has the lowest OH group on the left. Its enantiomer is its mirror image. So D-erythros, you just take everything that you just saw on the left here and you put it on the right over here. So this is the stereoisomer of L-erythros. So this is called D-erythros because the OH is on the right-hand side. So just a couple of interesting things I thought I'd point out. You guys know what spearmint is, right? And you guys know what, by the way, when does this lecture end? 20 after? I so badly want to go grab, I have the compounds in the back. I'll just tell you for now, and then maybe I'll dig them out for the next lecture so you can smell them. Carvone is actually what spearmint's molecule is called. It has an L form and a D form, okay? The L form is what we think of as spearmint. The D form is caraway. Now think about that. You change the shape of the molecule, you change the perception of the flavor and the odor. What does it tell you about your body?
It changes the shape of the molecule, how we digest it.
Well, okay, let's do this. No, it doesn't change, your body doesn't change the shape of the molecule when you digest it. When you smell it, right, The molecule goes up into your nose. So imagine this was one molecule, and I went up into your nose, and I grabbed the receptor, right? That receptor would activate, and then your body senses that as a certain kind of smell. When this one comes in, it grabs, it's not going to grab the same receptor because the hand shape is different. There's a pattern, maybe we'll lock and see, talk about enzyme. There's a pattern that the body will recognize as a certain odor. That's how artificial sweeteners work. They're a pattern that your body recognizes as sweet. And then now you have a left-handed version, you stick it in there, it's completely different. Okay? So what that implies, though, is that the receptors in your nose and lots of receptors in your body are also chiral. They have specific shapes that are created within the structure that are only activated by certain shapes of molecules. Your book doesn't talk about this next one. Well, they talk about this, but they get some of it a little wrong, I think. Here's L-DOPA. L-DOPA is a specific enantiomer of the precursor for dopamine. Now, when people have Parkinson's disease, a common treatment is L-DOPA. What happens when you take L-DOPA? Right, it goes into your body. There's an enzyme. It's called DOPA decarboxylase. And all DOPA decarboxylase does is take this carboxylic acid, converts it to carbon dioxide, and eliminates it. Okay? Called a decarboxylase because you're removing a carboxylic acid. This is dopamine. It's the neurotransmitter that's responsible for movement. And it's actually the restraint of movement. And so you have these nerves in your brain. It's called the nigral striatal pathway. They start down in your lower midbrain region and they go up into what's called the caudate, which is like if I were to able to take my head and then take the whole top part off, there's a little thing that's inside the ball that's on the inside. That's where the motor neurons end. And so what happens is those neurons die in Parkinson's disease, and then you end up not being able to produce enough dopamine. Turns out what the dopamine does in your brain is it shuts down other motor movements. So if you've seen people who have Parkinson's disease, what are they doing? They're doing this, right, without their medication. It's because they can't shut those things down. Okay? So one of the treatments, one of the very early treatments that was discovered was just give somebody L-DOPA, it's transported through the blood-brain barrier, and it's converted to dopamine from using DOPA decarboxylase. But again,
If I remember correctly, because this was like 7-8 years ago, but is dopamine the same thing where I know like if you don't have enough, then it's Parkinson's. If you produce too much, then it's schizophrenia?
yeah, so, dopamine, depending on where it's in your brain, is associated with all kinds of things. Emotion, rage, movement. People who have Parkinson's disease, though, also have degeneration of other neurons, like serotonin neurons, so they suffer from depression. So all these fetal grafts that they're doing to try to treat Parkinson's disease, they help with the Parkinson's syndrome, but they don't help with any of the other symptoms. Okay, so like the depression and other things that happen. Anyways, and this one, you might want to read it. I'll talk about it next time. We'll consider the lectures done for this chapter. Homework will be due on Monday.